to this special edition of Frequency Matters, the RF and Microwave Update. I'm Pat Hindle, here with my co-host Gary Lerude and special guest Tony Fischetti, and you're the Vice President and Chief Architect at MACOM now. Welcome.
Thank you. Great to be here.
So MACOM's been involved for decades in radar and phased array technology, but more recently you've done the MPAR project. Can you tell us a little bit about the history of that program?
So the history of the MPAR program is an effort that was started at MIT Lincoln Labs, funded by the FAA and the National Weather Service, to build and develop technology for a low-cost phased array to bring some economy of scale to the phased array building. The MPAR program has worked to build a planar phased array at S-band to try to drive the per element cost of the antenna down to the $100 to $200 per element range, which is significantly less than what current phased array antennas are today. The program was brought together with MACOM as the producer of the semiconductors to start, and then MACOM brought in some of their expertise to do the assembly and manufacture of the antenna aperture board and full-up antenna panel, as you see here in front of us. That design has now morphed into different applications and is expanded from S-band into other frequency bands. And the same basic construction, manufacture, and high level of integration have held for each one of the different projects that we're using this tile for.
So Tony, tell us a little bit about this right here.
So this is MACOM's 5G sub-6 gigahertz base station antenna, which is a byproduct of our MPAR design and is also a digital to the element version of the MPAR antenna using all MACOM semiconductors.
Can you talk a little bit about the innovations that you've introduced with this architecture for those of us that may be more familiar with a brick style?
The salient architectural point of this antenna is to remain planar, meaning that there is no slat or brick style into the construction. Everything is planar to the back of the radiating face or the aperture, and all of the electronics required to support the RF-TR module are all contained within highly integrated MMICs on the back of the antenna, again keeping it into a planar configuration.
So we've seen a lot of these planar configurations commercializing phased array. How does that drive down the cost and still keep the performance?
So one of the main aspects of driving the cost down is removing as many of the connectors as possible. By going into a planar configuration, we can then build the array in a printed circuit board style, which means we can do complete surface mount onto the back of the aperture board and contain all of the analog combining and manifolding, if you will, all within the aperture board itself. And also bringing all the voltage regulation and all of the capacitance down onto the back of the board will allow a single voltage to come in and be fanned out within the board. So driving out the connectors, driving out the complexity of cable harness, and truly keeping it planar allows us to have a very compact airflow design. Now certainly this, as you go up in power, heat dissipation changes, so you have to change your cooling medium. So from there we have to go to liquid, but MACOM has worked and looked at building similar planar construction with a liquid flow through to the antenna to allow that thermal path to be moved off and the dissipation to be handled.
Are you leveraging any of your optical technology in this?
So we are leveraging the optical side of our business as well. Through our data center business, we are working to do data conversion and optical transport right off of the tile, and we're bringing that through to have a very robust compact design. So one of the advantages that MACOM has is MACOM has built a RF to light portfolio of companies that allow us to take free space RF and bring it all the way through to an optical transport. So utilizing all of our data center technology and our data center expertise, we are working to build a fabric platform behind the array that allows us to move data seamlessly across an aperture.
Would you talk a little bit more about some of the applications, both on the defense side as well as, say, 5G that you mentioned, in terms of how this array would be used?
To take a look at where this technology is with respect to aerospace and defense and 5G, it's a very interesting concept. In the past, the A&D industry generated and developed technology which over time found its way in the commercial sector. You know, there are many examples of that started in the processing side and even in the antenna side, with phased arrays moving into Bluetooth and some of those products that we see today in our homes. What's happening now is this type of technology, by doing high levels of integration into the semiconductor side and building a planar design, is very attractive to the cell phone industry in terms of base stations. Base stations right now, you know, if you look at the number of 5G base stations that will get built and installed worldwide, is in the millions. That's going to drive costs significantly. Taking that construct and now bringing this type of manufacturing, this type of high integration, and bringing it back into the A&D world or the homeland defense world to be able to build very low-cost phased arrays to do a variety of missions, specifically air traffic control and homeland security and defense, is key to bring more surveillance and defense capability, you know, within people's affordability range. A paradigm is being created to where the commercialization of this type of technology, specifically in phased arrays, is going to be monumental in driving the cost of A&D programs down. And we see that worldwide. That this isn't a phenomena that sits here in the US. This is something that's very evident, you know, as we look across many countries of what they're doing, because they're all trying to generate a low-cost 5G solution.
Well, it sounds like a very compelling technology that has lots of applications on both commercial and military systems, and we'll be watching MACOM's progress very intently. So, Tony, thank you for coming to Frequency Matters and sharing this story with us.
Okay, thank you. Thank you for having us.